Welcome to FlexCache Volumes. This is a very interesting feature that has become recently part of Clustered ONTAP 9, but it had a predecessor in the past. I'm going to kind of skip over. I know we got a little bit of a shorter time frame than usual, so I'm going to skip over some of this introductions. But you know, QuickStart is a certified learning partner with NetApp, so I'm very pleased to be part of all that. And as mentioned, I've been doing this for some time. So one of my goals, or the goals here with this webinar, is to help you understand kind of how FlexCache volumes have evolved and what kind of problems that they're really designed to solve. It's a really, in a certain level, it might seem simple what we're trying to do here, but in actual reality, it's a very difficult problem from a technical perspective to solve. The basic idea here is that there is a need for a global file system. When we are collecting these massive amounts of data that are being generated from the Internet of Things, this is very difficult to manage these sort of quantities of data. Also, there is a greater and greater need to be able to access at least subsets of that data from different locations. And so that is the problem that we're really here trying to take a look at and see what aspects of that we can work or resolve with FlexCache Volumes. When we look at how we can manage accessing this data from multiple locations, there really are two basic approaches. One is replicating the data, so we have copies all over the place. And the other approach is file caching. And they have certain trade-offs. Each one has some advantages, but replication has some very significant drawbacks. When you make full copies of data, and you're separating this into different locations that maybe only need a subset of that data, you're wasting bandwidth and you're wasting space. How do I manage those replications is an issue. If it's scheduled updates, then my data is almost always stale at some level, okay? And it might become a major issue as we're trying to manage a lot of different relationships in a lot of different directions as far as replication goes. This gets very complicated. So, and then how do I protect that data as it's replicated in different places and being updated at different times? So the solution or the approach that NetApp is focused on right now is caching. And the basic idea is we present a kind of a virtual volume that is available in different locations. As users in those locations access that virtual volume, data is moved up toward them, okay? And so only the actual requested data is getting moved. So we're replicating on demand in real time. This allows us to focus the data where it's needed, and at the same time allows us to focus management of the data at the origin or source side. It gets much more difficult if we have multiple origins, okay? So those are some of the benefits or attractive sides to caching. But every approach has certain drawbacks. And one of the drawbacks to caching is how do you manage file locks and file permissions? We're distributing this data all over the place. Managing the locks is a very difficult technical problem. Okay. One of the things you'll notice as we're kind of going through this material is right now the emphasis is using, or the protocol we're primarily focused on is NFS version 3. And there are very good reasons for that. In NFS version 3 is a stateless protocol, and file locks are kind of loose, okay, in NFS v3. In our situation here, that's a big advantage, okay? So the other disadvantage of file locks is because we're replicating this in real time, that first read request is going to take more time. We have to copy that data up to our cache volume, and then that data is forwarded to the user that requested it. So the cost of that first read is higher. Okay? It seems like a new feature, but really this is not a new feature in ONTAP. This is something that we had back in the 7-mode days. And there are a lot of similarities between how this feature is implemented now compared to 7-mode. It's really, in many ways, solving a subset of the same problem. In 7-mode, the architecture was different. Of course, in 7-mode, we had standalone controllers. We didn't have clusters. And a lot of times, this accessing the data was being done at the physical controller layer. Okay? Now we do it at the logical machine layer with an SVM. In both cases, they're sparse volumes. Sparse meaning it only contains the active data set. It's not a full image of that particular volume. In 7-mode, the source and the destination were both flexible volumes. As we're going to see in a couple of slides, that's not the case in cluster mode, in ONTAP 9. The security style had to be Unix at the origin volume in 7-mode. And the only access was through NFS version 3. When writes occur, though we do a kind of a write around process, the write goes directly to the origin volume, and then any copies of that file which are distributed out in our environment, the changed files have to be invalidated so that we can reload them and everyone is seeing the latest copy. Okay, so that creates a certain amount of extra traffic, a certain amount of overhead. In ONTAP 9, we have tried to be much more flexible in our approach. So we're still replicating a sparse volume, but now that sparse volume can be replicated multiple times to multiple destinations. And this sparse volume is no longer a regular flexible volume, it's a FlexGroup volume. And that provides some very important benefits, which you're going to see in a slide or two. So we have a single flexible volume, which is the source volume, and then this FlexGroup volume, which is something I talked about in my previous webinar, this FlexGroup volume, which is actually the FlexCache cache volume. Okay. The big advantage here is inherent in the FlexGroup architecture is a layer called the remote access layer. And that remote access layer is designed to coordinate locality of the information inside the cluster. When we're doing a FlexGroup volume, we're going to extend that across clusters with FlexCache volumes. Okay. Unlike in 7-mode, that origin volume can have NTFS or Unix as its security style. And the origin volume could be accessed over NFS, but it can also be accessed over SMB. At the client side, the FlexCache volume can only be accessed over NFS v3. So you can see there are a lot of little rules on how this all works. Okay. Now, the goal is, or the kind of use case is, situations where we have relatively, and of course, that's an interesting word, relatively static data. We're needing to read that data in many locations, but we don't want to use this with a write-intensive application. Those writes have to go around the cache, updating the source volume. Then those blocks need to be invalidated in all the copies, and that takes time. Okay, so this is generally going to be applied to something that is very read-oriented. When that cache is gathered, when the data files are gathered in the cache, they're persistent. In other words, they're going to stay there until something pushes them out. Okay, and really what's going to happen is if you have sized this correctly, then the cache will gradually reach about 80 to 90% of capacity and sort of maintain at that pace. that should be basically matching roughly the working set of the data that those users at that location happen to be using. Once it passes that 90% threshold, then there's a scrubber that wakes up in the background, and it's going to identify which files have the least access or the oldest access. And that space is released to make room for new files. This cached volume does support auto growth. So if I need more space, maybe my working set has expanded, or I wasn't accurate about it up front, then it can grow that cache out at the location that's accessing the data automatically. Okay. This slide here kind of illustrates how that works. We have in 7 mode, this would have been a separate controller, and that controller has a volume. We'll just say, for example, that volume has 2 terabytes of data in it. But the active data is a much smaller subset. And so the users that are accessing that data through the cache only need to have enough space in the cache to support that active data set. And so that's what you see out here. That FlexCache volume in this case might be only 150 gigabytes, fronting essentially an aggregate or a volume that has 2 terabytes. This was executed in 7 mode with NFS version 3 semantics, and so because of that, it was tied very closely to NFS v3. Clustered on tap, the FlexGroup volume is the FlexCache volume is actually a FlexGroup volume. I know it gets a little difficult semantically there. And so it is made up of potentially many member volumes, but the big advantage of FlexGroups was this remote access layer, which allowed us to have pointers to different locations inside the cluster and basically transparently pull that data from whatever the respective location was. So we're going to extend that remote access layer and those links out across clusters instead of just within clusters as we did with a FlexGroup volume. Okay. So we take this idea and we're going to extend it out to possibly within a cluster. Sometimes there are workloads that people run that are extremely read intensive. And there's a limit to how many reads a particular node might be able to handle. So what I can do in those situations is I create this FlexGroup volume inside, FlexCache volume inside the cluster. And then using that FlexGroup architecture and the remote access layer pointer structures, we're going to be pointing back to the origin volume or source volume. And so all of those repeated reads that are happening are now offloaded, and they're running on a different node with different disks. And it's only needing space for the partial subset of the data which happens to be accessed or active at that time. And as that changes over time, this will dynamically update. So in Clustered on Tap, for a long period of time, there was an application that we called a data load sharing mirror. And that created a full copy at another location to offload those reads. That capability is still there, it's still supported, but it's been deprecated. Anything that we could do with load sharing data volumes, data mirrors, can now be done with these FlexCache volumes and done more efficiently. Okay. This origin volume can be any security style I need. It could be SMB. It could be a security style of NTFS when I'm doing SMB. It could be the security style Unix if I'm using NFS, or both. I mean, I can have both. I can access them from both worlds as far as the origin volume goes. Now the cache, at this point, the cache can only be accessed through NFS v3. But the goal is to be able to access this from SMB and from NFS version 4 and 4.1 later on down the road. So the structure that we have with this remote access layer should be able to support that capability. Okay. In the current implementations, all of the locks are managed at the origin volume. Like any cache access, we first have to populate that first read, and so that takes a little longer than if we were going directly against the origin. But then the subsequent reads will be satisfied from that local cache volume. Now, another option that we can do is we can replicate that data to another cluster. So that's what we see here. My FlexCache volume is in another cluster. This first cluster could be anything. It could be an all-flash FAS system. It could be anything, but it's, in this case, I'm representing it as a physical 2-node cluster. And over here, I have a FAS 270, which is kind of a smaller, lower-end system, which is perhaps in some remote location acting as a cache. Again, everything else stays the same. The locks are maintained and administered at the origin volume. Reads populate the remote FlexCache volume, which is in another cluster, possibly in a different part of the world. And then as writes happen, those writes walk around, they go to the origin, and the origin gets updated. If there are many copies of that file that might be cached at different locations, then the file caches are invalidated and they have to be reread. Now, this is also supported with ONTAP Select. With ONTAP Select, I can run essentially a virtual or software implementation of clustered ONTAP as a single node cluster inside of a VMware server, for example. Okay. And so now I don't need a physical controller. I can create this cache anywhere I happen to have an ESX server. Everything else basically works the same. Recently, this was also extended out into cloud volumes ONTAP. So now I can bring up an instance of ONTAP in the cloud and use that as my cache. Okay. Again, I create the relationship with the source volume. Certain metadata gets updated into the cache, so it looks like the files are there. Then you do that first read, and it starts to populate the cache. Okay. Subsequent reads then are satisfied here from this instance of ONTAP running in the cloud. Okay. And perhaps the clients that are accessing that data are also in the cloud. So I could use this to sort of burst into the cloud. I have a certain set of data. I need to run some CPU intensive applications against that data. I could bring up the compute servers in the cloud. I have my cloud volumes ONTAP instance running in the cloud. It will cache the data locally, and then the subsequent accesses are satisfied from cloud volumes ONTAP. I could have multiple caches. So imagine you have some sort of software development environment, and you have different teams of developers in different parts of the world. They're all working on the same code. And so I could have a physical cluster in some location. I could have ONTAP Select or running in a hypervisor at some particular location. I could be running cloud volumes ONTAP at a location. And all of these are pointed back to the same origin. And so this is where we get into that whole kind of concept of a global namespace. Everybody in different locations is seeing the same data. And as changes to that data happen, those changes are replicated out to anybody who happens to have it in a cached copy out on any of these locations. When they're retrieving that data after it's been cached, they're going to be able to access it with local area type speeds. and they won't have to wait when they're re-accessing those same files. There are a surprising number of applications for this. Okay? Again, it's a finite number, and the use cases need to be well defined. But it's surprising how many situations this can be helpful in. So I need to understand that I'm working with a certain subset of that data. And so I have to be able to estimate what the working set is. We have some tools where we can do that. And then you take that working set, there's going to be some metadata overhead and such, probably about 25%. So you take the working set plus 25%, and that gives you a pretty good idea of how big that cache should be. Remember that the cache volume is a FlexGroup volume. So it's made up of member volumes, and those member volumes could be distributed across a cluster. Okay? So we need to kind of have an idea how large the cache is to know how many member volumes we need to support that workload. And here you can see kind of how that works out. If we're talking about less than 100 gig, then one member volume would be enough. As we climb up in size, we add member volumes to reflect that. Okay. This allows us to parallelize those workloads and increase the performance. That is inherent in the FlexGroup architecture, which is why this was chosen. Okay. In order to use this effectively, we need to have a read-intensive workload. And basically, it needs to be about 80-20. Okay. Significantly more reads than writes. If it's a write-intensive workload, this may not be a good fit. Okay. One advantage is, of course, I can replicate this data out to all these different destinations. Okay, so I have copies and caches in different parts of the world. But they're all pointing back to the same source. So when we have this data, we have to be able to manage it and protect it. And the nice thing about the caching approach is that's all done at the source. So I can protect that data by taking snapshots of the source volume. I may need to replicate it with snap mirrors or back it up with snap vaults. All of that happens at the source side. Doesn't matter how many copies I have cached out across the world, everything is managed from the source side, okay, which simplifies things dramatically. Okay. Now, FlexCache is an evolving platform. This is one of those tools that if you're using it, you probably want to stay fairly up to date with what version of ONTAP you're running. Okay. It's been changing rapidly. Okay. And among those changes are things like, obviously, if we're replicating this data across the world, we're replicating this data into different environments, security becomes very important. And so now the origin and the source volume, or the source and the cache volume, can be encrypted. This was a 9.6 enhancement. We didn't originally support Q-trees. Now Q-trees and quotas can be enforced on the origin volume. That is a new feature in 9.6. We're increasing the number of cache volumes that a single node can support. And again, big feature 9.6. Incorporating the cloud is huge. One of the kind of use cases for this is there are certain workloads where customers really appreciate being able to burst up into the cloud. Normally, they need a certain amount of compute resources. Perhaps they have those locally, but then there are certain times where they need to surge up. So I could bring up the compute resources very quickly in the cloud and then cache that data into the cloud, and then I can run that workload from the cloud. Okay. That was a huge feature when this was introduced in 9.6. Okay. Metro cluster support happens in 9.7. A big change, I think this is going to be a huge change from the standpoint of user acceptance, is Originally, when this rolled out, there were licenses, capacity licenses for FlexCache. And to use more cache, you needed to spend more money. Now there's no longer a license. The cache has always supported deduplication and compression. But until recently, the cache had to be fully provisioned, which meant it could not do compaction. And I'm sorry I don't have time to really go into the meaning of all these various terms, but take the admin class, and I cover all this stuff. So as of 9.5, we can now thin provision the cache volumes, which means we can support compaction, which could save a lot of space, particularly if you are dealing with small files, lots and lots of small files. Compaction makes a big difference. Volume move was added in 9.6, being able to move my cache volume to different nodes in a cluster. And in 9.7, we now support auditing of reads. Okay? Again, if you think about this, this is not necessarily an easy thing to do. How am I going to audit the reads when I've distributed these files out all over the place? So they're working on these little complications, these edge cases one by one, and with each new version of ONTAP, more of them are addressed. Okay. Another problem that we have to face is if I'm distributing this data across the world, there could be a network problem somewhere. I know that's hard to believe. So if I all of a sudden can't reach the origin, the source, what happens? So it goes into what we call disconnected mode. All of the data which is already cached remains accessible. Okay? But if I make a request for something that's not in the cache and I don't have a network connection, it's going to time out. Okay? Writes will also time out. And they've made some modifications so that once that connection is reestablished, it'll automatically distribute some payload for the changed files that might have come in from other locations back up to that disconnected cache site. So again, this is actually a very difficult, these are difficult problems we're trying to solve. So there are certain use cases which really fit this model. Electronic design automation is normally an extremely read-intensive metadata, particularly metadata read-intensive workload. So that fits the cache model. Okay, we've got lots of reads coming from the same files, a lot of small files, complex directory structures. Imagine you're on a team of people and you're making a movie, and you're generating all of these CGIs and the graphics and all that kind of stuff. There are libraries that these different teams are working with. And so maybe they need libraries that are going to create a cloud in the sky. Somebody else has a library that needs to create water in a stream. And these people might be working in different locations, pulling the data from those libraries. Okay? Well, those libraries can be distributed through a cache, and they can all do their work locally and experience local area type latencies. Unstructured NAS. I have, huge amounts of data that are in home directories. Different people working in different offices all over the world. I could set up these caches and they will have access to their files in their home. And then when they make changes and writes, those will push through to update the origin. Everyone will see the new updates. Okay. Software builds, distributing tools for software development. If I have a really hot volume inside of a cluster, I can cache that on another node in the cluster and load balance that. Being able to burst into the cloud, as I mentioned earlier. Okay, cache that data in the cloud is another use case. There are also some use cases that don't fit very well. If I am making a lot of writes on my cache, those writes have to go around. They're going to hit the origin volume or source volume. If those files are cached other places, we invalidate the data in those caches. It has to be reloaded. This is not a good use case. It needs to be mostly reads. If I happen to be updating the origin volume intensely, okay, that's going to cause invalidations out at the cache. So again, that means a lot more reads to refresh that data. So that's not a good fit. Hypervisor data stores are not a good fit. So this is not something that you can use for everything. You have to understand the workload that we're trying to accelerate or the workload that we're trying to improve. FlexCache volumes are sparse volumes, meaning that they only need to be big enough to hold the active working data set out at that location. We can have multiple instances, multiple caches pointing back to the same origin, which gives us the ability to kind of step forward into that whole idea of a global namespace. Everybody sees the latest data no matter where they are, but we only need space to hold what they're actually using for a given period of time at a given location. And so that means they're going to get better performance because they're seeing a local copy, and everybody is going to see the same data at the same time as files change. So you can see how this is a fairly difficult issue, difficult problem to resolve. And as we work things out, I know the plan is as soon as possible to be able to do SMB out at the cache layer. But this is hard because of the way locks work with SMB. They're much more precise, much more intense, really. The control mechanisms are finer grained than in NFS, particularly NFS v3. We have the same problems with NFS v4. So by offloading this data in certain environments, I can dramatically improve performance. I've seen some really amazing numbers for things like renderings, doing it from the cache rather than doing the renderings from a remote site. In some cases, I could see this possibly being really useful for seismic data. I used to work kind of in the oil industry some. Seismic data was large, huge data sets, but they tended to, I think they would really cache pretty well. So they might be a good use case for that.